popular choice for a cross-section in a shaft subjected to torsion is a pipe, which is basically two concentric circles where the material is concentrated in the outside. And so you have an outside diameter and you have an inside diameter, and then here the shaded area is where you have material, and then it's hollow in the center. The stress distribution for this follows the same formula that we have discussed, except that there is no stress here in the center, and then the shear stress along the wall varies in this fashion. So it's as if you had the circular cross-section solid, except that you only use the values of R that are within the solid portion of the wall, right? The wall thickness. And so that's relatively easy to understand. Use the same formulas. They're just valid within the wall thickness. But why is this a good choice for torsional stiffness? So I'm going to illustrate this by an example. So say you have a solid circular shaft with 2-inch diameter, and that shaft has a polar moment of inertia given by this formula. In this case, equal to 1.5708 inches to the fourth. So this is solid, 2 inches. Now, we wish to find a pipe that has the same polar moment of inertia with an inside diameter of 2 inches, just like this, but we wish to find the outside diameter that will give us this same moment, the polar moment of inertia. So to do that, we recall that in this case we can use the subtraction theorem, which basically says we can compute the polar moment of inertia of the outside minus subtract the polar moment of inertia of the hollow section in here. So then that would give you pi diameter outside to the fourth minus diameter inside to the fourth divided by 32. We know the inside diameter, which is 2 inches, and we want to find the outside diameter. So we wish to get this number. So we put this number in here, 1.5708 times 32 divided by pi plus inside diameter, which in this case is 2 inches, to the fourth, all of that, the fourth square root, that gives us the outside diameter. Okay. Multiply by 32, divide by pi, add di to the fourth, then take the fourth root of that. If you do that calculation, you end up with this number, 2.38 inches approximately. So this tells you that with an outside diameter of 2.38 inches and an inside diameter of 2 inches, you get the same polar moment of inertia, approximately within 2 decimal places, of a solid circular cross-section of 2-inch diameter. Now, The reason why this is so effective is that if you compare these two areas, you will find that this area is significantly larger than this, which basically means you need a lot more material here to achieve the same torsional stiffness in comparison to this. Actually, let's do the calculation. In this case, the area of this would be pi diameter square to the fourth. Boils down to this, right? In this case, the area would be this. Again, by using the subtraction theorem, where we take the area with the outside diameter and subtract the hollow area from the inside, right? And so if you substitute this, you get 2.38 square minus 2 square divided by 4. That boils down to 1.3007 inches square. If you compare that number with this number, you see that this one is only about 42% of that. So with less than half the area, you can obtain the same torsional stiffness. So this is the reason why pipes are an excellent choice when you need to resist torsional stresses.